Hello friend, welcome to Data Lux. In this video, we are going to discuss a question from the linear algebra from the GET DA paper, which is 2 marks and MCQ type. The question here says, let A belong to R n by n, that is the n cross n matrix or square matrix with real entities, right? Such that A cube is equal to A. Then which one of the following statement is always true? First one is say it A is invertible. Second is determinant of A is 0. Third one is the sum of all diagonal element of A is 1. And the last one is A and A square have the same rank. So we can check here by using this property here by using this equation. That means A cube equal to A. So we can write here this as A cube minus A equal to 0 or a square minus I equal to 0. Or we know if in term of polynomial as by using Cayley-Hamilton theorem, every square matrix satisfy its characteristic equation. So here we can write in the term of polynomial p of x equal to x square minus 1 here, and this annihilates. Or further we can write in term of the characteristic equation, or we can say here every eigen eigenvalue eigenvalue lambda of A must satisfy in term of lambda. We can write here lambda square minus 1 equal to 0, or you can write here lambda minus 1 and lambda plus 1 equal to 0. So from here we get what we get here, lambda equal to 0 minus 1 and 1 here, or we can say lambda belong to minus 1 0 and 1 here, right? So if now let us check first condition in by using this. So if we have lambda equal to 0 1 as a eigenvalue here, that means it might be a equal to 0. So this may be a case here. So if this a equal to 0, that means a cube equal to a, this equation, this a satisfy this equation. So if this satisfy, that means a equal to 0, that means it is a singular matrix. So A is singular matrix right here. So A is singular matrix, that means A is not invertible. So in this case A is not invertible, right? So here our first option is, that is the A is invertible, that is the incorrect one. Now if you see the second option, B determinant of A is 0. So what we can say here, in case of second option, this is the first and this is the second. So second option, what it say, determinant of A is uh, determinant of A is 0 right here. So this is also not always true, not always. Why? So we can check here by using the if we can this is the, as we know, lambda have eigenvalue, lambda have plus minus 1 here. That means there may be a chance that a such that a equal to I here. So a equal to I here, that means in this case we'll get the determinant. So if a equal to I, that means we can take a such that identity matrix, that means 1 0 0 0, like 0 here, and 0 1 0 0, and dot dot, or 0 here 1. So if this is the n cross n matrix, that means as we know, in this case, and the determinant will not get here uh, 0 here. So in this case we'll get the determinant here, in this case, the determinant of A will be also, if lambda equal to plus minus 1, that is the here, this will be also plus minus 1 here. So this also not satisfying this condition, that is also this one in the false statement. So second option here is also, this is also false. Now let us see the third option. Sum of the diagonal element of A is this is the 1. So as we know, sum of the diagonal element also known as the trace of a matrix A here. So as we know here, this what it say, uh, trace of A equal to 1 here, right? So further, if we take such matrix, that is the identity matrix we have. So if we have A equal to 1 0 0, like this one, 0 and 0 0, here is 1 0 0, and this is the one here. So in this case, this is also n cross n matrix. So in this case, trace of A will be, this will be n right here. This will be n, as this is the 1 plus 1, uh, 1 plus 1 plus 1 dot dot plus 1. How many time? This is the n time, right? So this is the n time, that means summing up these n time, that will result n here. So we have what question say, trace of A, that is the one, that is also false statement. So third is also false. Now let's check the fourth option here. This is also false here. If you check the fourth option here, A and A square have the same rank. So these three option is the incorrect. That means this is the correct option right here. But we have to check. We can check this why this is the correct. So for in that case, we can assume here what we can write here in term of the as we know, we can write in term of the diagonal element. So t equal to, we can write here diagonal of lambda 1 lambda 2 dot dot lambda n, with each lambda I belong to minus 1 0 and 1 here, right? And further, what we can write here, we can take a square of this d square. So in case of d square, this also is square of these entities. That means lambda I square will also belong to, so when we square minus 1, this will result into plus 1, and 0 square also 0, and 1 square 1, that means this will belong to 0 and 1 here, right? So here every here this will result in the positive numbers. So here we can conclude that the position, if we check the position of the position where D has non-zero, has non-zero entities, entries are exactly those where D square has entry 1, those where D square has entry 1, right? So by using this, we can get there. So in this case, the number of non-zero diagonal element of D. So non-diagonal, non-zero diagonal element of D, non-zero diagonal element of D has equal the number of non-zero diagonal element of the D square. So by using this property, we can say here rank of D will be equal to rank of D square right here. And what we know, uh, by conjugating with the P. And what is the P? P is the we have the P is the invertible matrix. So P is the invertible matrix. That means we can, for example, as we know here, A is, you can write A equal to P dp inverse right here. So if this preserve the, by conjugating this preserve the rank also. So by, we can write by conjugating with p. So this will preserve the rank. That means this will further with can uh, produce here rank of A will be equal to rank of A square right here. So this is the true. So here we have, we calculated that A and A square have the same rank, right? This is the true statement. So that's it from this video. Thanks for watching.